continue today what we started last time. Okay, so we were doing stability of equilibria of nonlinear 2x2 systems. So here is a nice generic system x dot y dot equals f of xy, g of xy. First thing is first find the equilibrium, then compute the linearization, meaning we take the partial derivatives, right? So A is formed by the partial derivatives of these vector field functions, okay? So dg dx, dg dy, but you have to input the point. So is all these guys calculated at the equilibrium, yeah? So basically this matrix has entries, numbers, not functions, okay? So it's really, it's like a matrix that, for example, A could be, right, 1, 2, 5, 9, okay? So it has to have numbers inside, not something else. Okay, we'll do anyhow, we'll do a few so you'll see how they're calculated. It's straightforward actually as a calculation. And then we calculate the eigenvalue of this matrix, and then we have a classification of the stability, right? So basically this classification is based on some linear algebra fact, is the fact that we can change the basis, the representation of A, we'll put it in a different basis where it becomes diagonal, and that's what is done in linear algebra. And then using a certain change of variables, we can turn that system in X and Y into a system little x, little y. So in capital X, with a change of variable, we turn it into a different variable via, y is p minus 1x, where p is the change of basis matrix. And in this way, long story short, is like last time, we managed to write the system in a diagonal form. And once we write it in a diagonal form, we can actually solve it and see how the solutions look like. So this is the example from last time. We had the system in X and Y. Here is a linear system 2x2. Then we computed the eigenvalues. And then basically when we change, use the change of matrix, change of basis matrix, the diagonal form of this A becomes 3, 1 on the diagonal and 0, 0. And then we write the system in U and V, new variables with this 3 and 1 on the diagonal. And the diagonalization basically leads to the fact that the system decouples. We can actually put our hand on the solutions, and then going back to the original coordinates, we see what the original x of t looks like, and then consider the stability of, the linear system in 0, 0, so we know what is going on. So here, anyhow, we did some of this last time, right? For the eigenvalues positive, eigenvalues negative, and today I'm ready to show you what is going on when the eigenvalues have different signs, okay? Okay, so here we're in little 3 case when this A, right, which is some A, B, C, D, has eigenvalues. They're both real, but now one is positive and one is negative. So this leads, if you're going to look in your notes, to a system in UV that would look, right, with these guys on the diagonal, but one is positive, one is negative. So you'll have a U dot is lambda 1 U, and V dot is lambda 2 V. But this is, for example, right, would be like U dot 1 is positive, 3U, and V dot 1 is negative, 2V. And then when we solve these guys, this is a C1E at 3T, and this is a C2E at minus 2T. And the main question we want to answer is what is going on with this U and V as T goes to infinity. So as you can see, well, in the general case, right, would be something like this, right? And immediately, because lambda 1 is positive, this one, as t is going to infinity, will increase, right? So could be plus or minus infinity, depending how that constant is with plus or minus in front of it. And v of t, so, you know, you can look at this and this to figure out why I'm writing what I'm writing, right? Okay, so this one, because lambda 2 is negative, this will go to 0, right? Okay, so this means, right? So remember, this is the transformed system, right? So from A, we go into P minus 1 AP, which is with lambda 1, lambda 2 on the diagonal, right? And then this is the system that regards that Y is P minus 1 X or something, right? Okay, where P is the matrix with the eigenvectors on the diagonal. What I want to tell you is the following, is let's understand how this one is going. So if I'm doing now the picture in 3D, so we're looking at this as the solutions of the stability of the solutions u of t equals 0 and v of t is 0. See, this will be the equilibrium x naught y naught in the y coordinates. So we just shifted it to be the origin. So this would be, right? So this is a u naught and the v naught. So if I'm to do a drawing in 3D about this stability, so let's say this is the t-axis, and the red thing is really our equilibrium, right? And here are the coordinates v and u. And I want to draw these guys. What is going on? So if, for instance, C2 is 0, then I'm going to stay in the plane UT, right? So I'm going to be in the plane UT with this kind of solutions. And as t goes to infinity, right, they're kind of going up. So let's see how we can draw this. So in, right, I'm thinking here separately UT, right, and we have U is C E at 3T or something, right? So it has to go up, right? So there are solutions that are going up to infinity. So if I want to draw these guys, right? So, okay. And then if I have another initial condition, I would go something like this, right? So what am I doing? It's backwards. That's why I hesitate here. Oh, silly me. Okay. So how do we do T and U, right? So U is C E at 3T. So now it's going like this, right? Now it's good. I'm like, what the heck is going on? Okay. So in this picture would be something like, so U is here, right? And now, because I have to flip it somehow, right, in order to draw. So it would be something like this, right? And if it's on this side, right, no matter, but it stays in the plane UT. So these blue curves, you know, would correspond to the case C2 is 0, and they're curves that represent U of t of the form C1 E at lambda 2t. Yeah. Whereas, okay. Now, if I want to draw curves that have C1 0, so they just stay in the plane VT. So here is T and here is V, right? So if I'm doing them separately, so these guys are like V is C E at minus 2T, right? So they would look something like this. Boom, right? So they die as T goes to infinity. So now if I'm drawing them in this plane, they're kind of doing exactly kind of the backwards thingy with respect to the other one. So all I'm doing here, I'm trying to understand what's going on with the dynamics in actually in 3D. So I repeat, these green curves correspond to the case C1 is 0 and V of T then is something like C2E at lambda 2T. You guys with me? So all I'm doing, I'm just drawing some curves in 3D, putting them separately. How do they look in 2D? And then, you know, moving them in the, on the drawing on the left-hand side in 3D. And I'm trying to obey a color code so you guys understand. Okay. And in the middle here, not moving at all, this red thing is U of T equals V of T equals 0 is the equilibrium. For, if you want, right? So this is equilibrium for y dot equals lambda 1, 0, 0, lambda 2, y. Yeah. So it's in the shifted coordinates, in the coordinates where the, you know, where we diagonalize the matrix. Okay. So that's what we're doing. Now, of course, we should put the stuff together. So this is, you see how these vertical planes, they stay, we call them invariant, because if a solution starts in one of these planes, it just stays there forever. So for instance, this blue one, right? It started in the UT plane, but then it stays in the UT plane forever. And this is because basically C2 is 0. So C2 has the V equation, the V part is just null. Right? And the same here. Whereas, you know, in the one with the light green one is the other way around. But these are very exceptional cases, right? You know, that they keep invariant these planes. So a generic initial condition would be somewhere in the middle, right? Somewhere, I don't know how to make, like here, okay? And then what does it do to the solution? So it's the combination of the two, right? So this pinky one would correspond to something like, you know, it's a point of coordinates C1 E at lambda 2T and C2 E at lambda, or, you know, a curve of coordinates C1 E at lambda 1T and C2 at lambda 2T, right? So that's the U and V coordinates, right? The entries. So what does it do as time varies? Well, because it's these two guys and none of them is 0, right? And one is growing when we're going to infinity, one is growing when t is going to minus infinity, because they are kind of in the mirror, right, with respect to the horizontal. Well, what it does, it really does something like gets close, punches in, and then it gets far again. Okay, so here, kind of the same. So here. So what I'll do, I'll flip the page and redo this picture and then see what is going on in the face plane. So once again, here is the 3D, right? So there's the V, there's the U, there's the T, the equilibrium U equals V equals 0 is here. So this is the equilibrium, right? It doesn't move, all right? And now we had the light blue ones, right? They were in the UT plane. Here is one. Here is another one. Then we had the light green ones in the VT plane. Okay, so actually these guys, as t goes to minus infinity, they get close to the, so they're kind of in the mirror. Okay. Something like that, okay. And then for the other guys, they're kind of backwards. Yeah. Whereas a generic one that I did with Pinky, it was something like zoop, punch it in, and then it goes in a different way. Whoop. Okay. So now if I take this picture and I'm looking at it from above, and I don't see the t-axis anymore, I just see the UV plane, what will I see? Well, let's see. So this is the UV plane, U and V, okay? I see in the middle the red dot that corresponds to the equilibrium. Right? And then I see for the blue, the light blue thingies, they're on the, they will be only along the U-axis. So these are the curves that are drawn with the light blue. And this t goes to infinity, they go away from the red dot. Now I'm looking at the light green curves. As t goes to infinity, they get closer to the red dot, and they are on the OV axis, on the V axis, right? So as this t goes to infinity, they get into the red dot, into the equilibrium. Okay? Whereas a generic curve that is done with pink, what it does is, well, it gets kind of close here. It has a point of approach, right? But the rest of it is just kind of following the other two curves in the past and in the future. So in the past was somewhere here, and in the future is just following the other guys. So it's something like that here. If you want, I can put the arrows on this too. Okay. And here, once I put one, you know, what is this other one doing? Oh, what is it? It's kind of doing the same, right? So it has a point of closest approach, but then, you know, in the past was, right? Whereas it wasn't in the future, it's just going away, right? Something like that. Okay. So there you go. And that's how these pictures are obtained, actually, with this kind of thinking. Okay. And now comes the A+ question. What kind of equilibrium is this one? Stable or unstable? You can type it in on the chat, guys. Any answer is a good answer.
Unstable?
Stable or unstable? Unstable, because it doesn't get in, right? So the stability is only when the curves are getting in, or they just stay around, they don't go away. Whereas in this case, it's clear that we have this blue one that is just, you know, pushing out, and then it's carrying the other guys with it as well, right? So this would be an unstable equilibrium, and it's called to be a saddle point. Okay. All right, and now comes the question is, what is going on with, so this is in the shifted coordinates. This is in the y system, right? In y dot equals lambda1, lambda2, 0, 0, y system. That's what is going on, right? So in this system, we have, right, the 0, 0 equilibrium, right? Which corresponds to the original, right? X naught, Y naught equilibrium, right? So now if we're going back to the XY coordinates, how this picture would look like? Because it won't be as straight, right? This is really aligned vertical and horizontal, right? But that one is not aligned the same. So can we figure out how that one is aligned? And the answer is yes, that's where those eigen vectors are coming into play. So here I have an example, and I'm putting the example because I have the calculations done, not that. So here is X dot, Y dot. This is a linear system. 1, 0, 2, minus 3, xy. So A in this case is 1, 0, 2, minus 3. And then we end up with lambda 1 to be minus 3, and V lambda 1 is 0, 1. And lambda 2 to be 1, and V lambda 2 to be 1, 1. Okay. And I'm going to slow down with my explanations, actually. All right. So this means that in the UV coordinates, we end up with minus 3, 0, 0, and 1. Yeah. From where we understand that U of t would be C1 e at minus 3t, V of t would be C2 e at t, right? From where we deduce immediately that picture in U and V coordinates. In this case, it will be turned around. So U is the one, okay, so I should obey the, U is the one stable, so it goes in. And V is the one unstable. I'm trying to obey the color code here. Right, and the red dot in the middle, of course. So now if we're doing the, right, the curves, the phase curves, right, we immediately see, we actually can see that this is a saddle, right? So it's an unstable equilibrium, and it's a saddle. Okay, I think everybody is okay with this, right? But now we're going back to the XY coordinates, right? So in XY coordinates, if you remember from last time, right? So in here we have X of t, Y of t. This is C1 e at minus t, V of lambda 1 is minus 3 if you want, plus C2 e at t, V lambda 2 is 1, right? So in other words, this is C1 e at minus t 3t 0, 1 plus C2 e at t 1, 1, okay? So instead of the UV, right, vertical and horizontal, now we have these vectors, V lambda 1, V lambda 2, that would play the role of these straight lines that go in and out of the equilibrium, if you want. Okay, so in an XY coordinates, in this case is still 0, 0, the equilibrium. Okay, so here is in X and Y, right? So I still have for this one, I'm going to put it up here. Okay, so here it is, right? But now I have this vector 0, 1, so X is 0, Y is 1, so it's the vector of direction, okay. The vertical direction just so happens. So this is the one that is with minus 3, so it goes in, okay. And the other one is aligned to the vector, the eigenvector 1, 1 with the other one. So the other one is right? X is 1, Y is 1, so it looks like this. Okay, so if you want, this green one is actually the eigenspace corresponding to lambda 1, right? So this is span of V lambda 1, or lambda 1 is 3 if you want, right? Whereas the other one, right, this is the span of lambda 2. Span of V lambda 2 equals 1, right? So basically when we change when we diagonalize the matrix, we just straighten up stuff, right? You know, but those subspaces are invariant when we apply this linear transformation given by A. I'm not getting into linear algebra more because that's not part of this course. What you should understand is that, look, we're saying that that's a saddle and whatever. And to be honest, we don't need to go through this, okay? We don't need, and actually we will not go through this. But the reason why from here we get this is because one, you know, goes through this kind of thinking, logical thinking. So for your test, if you want to be just practical, what do you have to do? Oh, you have to compute some eigenvalues and some eigenvectors and use Maple for that, if that's what you want to do. And then, you know, kind of make me this figure. And you already know that these eigenvectors, you know, they're just there to as invariant directions. And then, you know, you just put the picture together. But why the picture is like this? The reason is all this story in here, right? There you go. And of course the nature, so we just deformed the picture, you know, from UV to XY, or the other way around, from XY to UV. Qualitatively, it stays the same, right? As we say, the topology is the same, whatever that means, or your math students, you know. But we don't have a topology course, at least not now, right? Maybe later. So, you know, it's just a deformation of the dynamics, but it doesn't change its character in any way. So this point here, right, this equilibrium in the XY system is still an unstable equilibrium. And it's a saddle. So nothing is changed, it's just deformed, as I say, right? So in other words, we change the coordinates to make our life easier, to see things better, right? But in truth, we don't even have to do it. We just have to compute some eigenvalues, eigenvectors, and make a picture, right? That's what it is. Okay. So there's that with that. And now in principle, we should continue with this classification, right? So if you guys copy it, if not, you'll have the notes. So, you know, we had here, how many cases they were listed by me here? Where is it? Sorry, I have to flip this. See, we have, so we just go through this case, right? Case 1, when we have a diagonal matrix lambda 1, lambda 2. We should go through this one, and this one. However, I will not do this because people did it for us anyhow. So I'll just show you what is in your textbook, and what we have, you'll have access during your test as well too. So how people, because this is always, you know, it's a 2x2 system, and we always get a quadratic in lambda. They said, look, you know, I can do the classification rather computing the eigenvalues every time, just looking at the coefficients, okay? So here is how the story goes, okay? For a matrix A, so I'm gonna put here note on eigenvalues, on 4. Okay. 2x2 matrices, okay? Okay, so let's say we have a matrix, A, B, C, D. Okay, and then we want to find lambda 1, lambda 2. Okay, so we have to solve that of A minus lambda I2 is 0. Okay, in other words, determinant of A minus lambda B C D minus lambda is 0. Okay, so i.e. we end up with this equation. Okay, so after we do the computation, that's what we're going to get. Okay, and we have a quantity of interest is the discriminant. All right, is delta, which is a plus d squared minus 4ad minus bc, right? So basically when we write the roots, right, you know that everybody kind of knows this, right? Over 2, right? That's what we do. Right? Okay, so now the discriminant positive or negative gives us, you know, real roots or non-real roots. However, it can be shown, okay, so some of them are seen by eye, that if we do the sum of the roots, no matter if the roots are real or not, the sum of the roots is going to be a plus d, and let's call it p, so we can use the table that is given in the book. And then the product of the roots, right? So if we do here, you know, lambda 1 plus lambda 2, and, you know, the product, it will be AD minus BC, and let's denote it Q as in the root. Okay. So now we're going to do a kind of reasoning along the line. If delta is positive and we have the product Q. Okay, so Q is the product of the roots, right? Positive. This means that lambda 1, 2 are real and they have the same sign. So now if they have the same sign, this means that we can look at their sum and deduce if the sign is positive or negative. You see what I mean? So we can basically classify the roots of this quadratic here just looking at these three quantities. We're looking at the discriminant and we're looking at the product and the sum of the roots. Okay, without computing the quadratic, just looking at these quantities. So for instance, so I'm going to flip the page and write the essentials again. So here the essentials are, we're playing with this equation. Okay, you don't have to write them again. Okay, and then we have delta, right? So I plus d squared minus 4ad minus bc. And then we have the sum of the roots, a plus d. And then we have the product of the roots, ad minus bc. Okay, so now for instance, case 1, when delta is positive, this means that lambda 1 and lambda 2 are real numbers. And now we have case little I. Case little I would correspond, or actually would be like this. If Q is positive, this means that lambda 1 and lambda 2 have the same sign as I wrote on the other page, right? But now it could be if P is positive, then we deduce that lambda 1 is positive and lambda 2 must be positive. Whereas if P is negative, then we deduce that lambda 1 is negative and lambda 2 is negative because they have to have the same sign. And then we go to case 2. If the product is negative, then we deduce that lambda 1, let's say, is positive and lambda 2 is negative. right? And I don't have to say more in this case. I could say, well, actually, if, I can even do it further. If P is positive, this means that the lambda 1 who's positive is greater than the absolute value of the one that is negative. You see? And this is without solving, it's just looking at the coefficients, right? So if P is negative, then the one that is, the root that is positive is less, in value than the absolute value of the one that is negative. So here would be like 3, so lambda 1 is 3 and lambda 2 is -2, right? Whereas here would be lambda 1 is 3 and lambda 2 is -5. Okay, something like that, right? That's what I mean. Okay. And then having this kind of classification, we can attach to it the results that we know from our dynamical systems, whatever, right? So when then lambdas are positive, in this case, right, the equilibrium is unstable, right? So in this case, okay, unstable equilibrium, and it's a source or unstable node, okay? Whereas in this case, it's a stable equilibrium and it's a sink or stable node, okay? Whereas in this case, no matter what it is, doesn't really matter. In both cases, this is an unstable equilibrium and it's a saddle. And that's what we did, in detail. But now the story continues, right? So the story continues with the other cases, right? So 2 would be when delta is 0. So in this case, lambda 1 equals lambda 2 and is in R, right? They're both real. Okay. And now you have something like, so basically you have to look, I think, only at the sum, right? So because the product will always have the same sign, because if they're equal, they're either both positive or both negative, right? So this guy is always will be positive, right? So we don't have to look at it. But what we're gonna have, we can look at the P, right? So P is lambda 1 plus lambda 2. And then we have, if P is 0, right? This means that lambda is 0, right? So both of them. So maybe I could call them lambda 1 equals lambda 2 equals lambda, right? So in this case, we have again an unstable equilibrium, and it's an unstable degenerate node. It's called degenerate because it has the eigenvalues equal, right? But the behavior is the same. So I'll have some pictures in a second, right? The book. And then P is negative, then this case lambda is negative. So in this case, we're gonna have a stable degenerate node. Okay. This is the same also for the third case. Okay, so in both second and third case in our initial, where is it? Here. I'm sorry, I'm flipping, but I have to. Where it is, it's somewhere. Here, see? In both second and third case, we had the lambdas to be equal, okay? So we're covering directly with delta equals 0. both of them, and it's still degenerate. Actually, these cases can be solved by hand in systems, so you don't have to kind of memorize this stuff. It's done, you know, the system is decoupled and it's two equations that look the same actually, or okay. And then the case 4 would be when delta is negative. In this case, we have lambda 1, 2 to be complex conjugate. And in this case, rather, you know, I just do it like this because this is much straightforward, you know. So if what's going on here, you know, for you to understand is that x of t and y of t in this case will look like something v c1 v lambda, well, we're lambda 1, let's say, e at minus 2t cos, okay, no, it's too complicated in this way. Okay, so what I want to say is that in this case, solutions, you know, behave like e at lambda t cos beta t and e at lambda t sine beta t. Okay, and why am I, you know, I'm putting this behaves like. Why am I doing this? Because now you see, where do they go, these guys? Do they go to 0 or not? Well, as t goes to infinity, so actually I should put u and v, yeah, u and v. Depending, if alpha is positive, this will go to plus or minus infinity, right? It will diverge if you want, okay? So, right, because this guy will go to infinity, right? So if you want, you know, I can say, okay, something like that. So as t goes to infinity. Whereas right, so if this is, if this alpha is positive, right? Whereas if alpha is negative, is a different story, right? So if we have u of t to be like e at minus 3t cos 2t, clearly this one goes to 0 at t goes to infinity, because in this case, alpha is negative. That's how the stuff is done. Okay. Whereas in the other case, right, it's actually, this is divergent. It's not even plus infinity, it's just divergent, right? Because it's plus or minus, depending how cos evolves as well, but it goes like blah, blah, blah. So basically for u of t in this upper case, what you're gonna have something that does like, right? It diverges, right? Whereas if this alpha is negative, then, right, well, let's say sine beta t, this will go to 0 again, right? So in this respect, we have the following, right? We have if, right, v of lambda, which is alpha, is positive, then the equilibrium is unstable, okay? And it's a unstable spiral, I think it's called. Okay, and it looks like this. So if I'm doing it in the XY coordinates, doesn't matter wherever the point is here. If it's in 0, then we have a trajectory that okay, I want to see something, just a second. That does something like this. It comes in and it goes out, right? Okay. Whereas if this is negative, then we have a stable spiral. Okay, so it's doing it exactly the other way around. Okay. So it's, but now it goes in, right? And there is one more case. Okay, so I'll wait for you guys to write. Right, so we have finally, and not the less, actually this is the most important one in a way. If this is 0, so you have basically lambda 1, 2 is plus minus I beta, right? So you're gonna have u of t to be cos beta t and v of t to be like sine beta t. What happens, this is exactly like in the systems that we did before. In this case, the solutions are staying, I'm gonna do it in 3D now, are staying on a cylinder. So if this is the equilibrium in T, right? We're gonna have right? The solutions won't go away, but won't come close either, right? So they will just stay. So you can see actually that the kind of u squared plus v squared is a constant, would be a constant, okay? So can put here a C1, C2, so we will have something like this. So they're staying on an ellipse of, what's this, right? It's an elliptic, right? So on the base here is in an ellipse, and then it just stays on this tube, right, with elliptical base. So if I'm looking in the, just in the view v coordinates, right, I will see here as the equilibrium, and for us here would be that guy like that. So what we're gonna see, we're really gonna see just this. Okay, so I have to decide which way, let's say is going this way, okay. Okay. Ah, it's backwards, of course. Oh, of course, this is backwards. Okay, something like this, and then I'll turn this one around. Okay, so what we're going to see, in this, right, in this plane here, the equilibrium in the phase plane will be surrounded by these circles, right? These orbits that are like circles or deformed circles. Okay. Now, this story that, you know, I put it down because I have to put it down. It's actually the table of all this stuff that you will learn to use it, because I'm not asking you to memorize it, is on your, on my learning space there. And here I'm gonna open it for you, is in that file at page 70, and this is the classification in terms of delta, the discriminant P and Q, right? So P is on the horizontal, that was the sum, and this is the product, right? Something like that. And you see, if the product is negative, all equilibria are unstable and they're saddles, right? If the product is positive, I don't know how well you can see, guys. I hope you can see, right? Then you have a variety of stuff. So, you know, if delta is negative, you have a stable spiral. You have to read what is here, right? And just see where you fall with P and Q and the delta, right? So if delta is positive, so in my mind, you know, I'm not really thinking on the table, but this is because this is my job, okay? but that's why, right? So delta positive means that the eigenvalues are real, right? So for me, if they're real, this means that it can be, it's either they're both positive, both negative, or one positive, one negative. If they're one positive, one negative, that is clear, it's saddle, right? It's right there. If they're both negative, then this means that all are going in, because you see, I always keep in mind E at lambda t. That's my key. That's what I keep here, right? If lambda is positive, it's like E at 3t is going to infinity. If lambda is negative, right? So you don't see what I'm writing, of course, and I'm silly, right? So here, okay, I'm seeing my screen. Yeah, okay. So I was saying, this is my secret. That's what I keep in mind, okay? Because, you know, solutions behave like these guys. So if they're both positive, then they're going to infinity is done. If one is positive and one is negative, it's still one is going to infinity is done. If both are negative, then this is going to 0, so it's stable. You see, that's what I keep in mind. That's, you know, my secret. Now, if you don't want to keep this, you know, in the back of your mind, it's fine with me. Just look in the table, learn to use that table. Okay, I'm going to go back to the table now, right? And read from here, right? So compute this quantity delta P and Q for every 2 by 2 matrix there that you do the eigenvalues, and you read what is there, right? So with this being said, I actually want to do one exercise with you just on the top. I think we do have time. And I didn't work it out. I'll just do it with you. Okay. We'll just work it together to see what is going on. Okay. So here. Okay. There we go. Okay. So I'm just picking an exercise, and then we're going to use that table. Okay. So here it's from the set I assigned you. Exercise 2.3 has more subpoints. It has 10, but you know, anyhow, I'm picking one. Okay, 2.3. So it's at page 80 from that file. And I'm taking here exercise 6. Okay, 6 Roman. Okay. And here we have x dot equals minus 6y plus 2xy minus 8. And y dot is y squared minus x squared. And all what we want to do is to find the equilibria and their stability. Okay. So I'll find an equilibrium and I'll do the stability for 1 or something. And then you do the rest. Okay. So first is first, right? Equilibria. Okay, so equilibria are found by doing right-hand side equals 0. So in this case, we have to solve this wonderful system, right? And as I said, I didn't do it, so we'll do it together, okay? So this means that x, for instance, is, or y is plus minus x. Okay, so here I have case A, let's say, with plus minus 6. Okay, so let's say y is x, then we go into the first equation. So let's call 1 into 1, and we get minus 6x plus 2x squared minus 8 is 0, or x squared minus 3x. Oh, I couldn't choose a better one. Okay, minus 4 is 0. So x1, 2 will be 3 plus minus the root of 9 minus plus 8. Whoa. Okay, yeah, I really picked. Anyway, that's life, right? So 3 plus minus root 17 over 2. Did I do something wrong? I should open the chat because I'm prone to do mistakes here. Okay, so we have equilibria at xy, right? So we'll have x, e, y, e, right, equals, okay, let's put them 1. Okay, Okay, so 1 will be 3 minus root 17 over 2, and y is equals to 3 minus root 17 over 2. That's 1. And then we have the other one, 3 plus root 17 over 2.
Professor,
Hey, what did I do?
I think it's 9 plus 16.
Okay, 2,
So it's
9
for AC.
plus, yes, you're absolutely right. Okay, let's change. Oh, which makes it 5. Okay, I was wondering. Good, thank you. Okay, so there you go. I feel better now. Okay, all right, good. So it's 3 plus minus 5 over 2, right? So we'll have minus 1, and then we'll have 4, right? So we have minus 1, and then we have 4, 4. And then case B, when y is minus x, then again into equation 1. Okay, we have minus plus 6x plus 2x squared minus 8 is 0. So x squared plus 3x minus 8 is 0. So again, x1, 2 is minus 3 plus minus, not 8, 4 here, 4. 9 plus 16 over 2. So minus 3 plus minus 5 over 2. So we're going to get the minus 4 and the 2 and the 1. Good, better. So we have x3, 4, x3 and y3. Okay. Would be minus 4 and 4. And x4, y4 to be 1, 1. Okay. Progress has been made. At least we did the equilibrium. Okay, that was the easy part, right? 2, we're going to compute the linearization of this thing, but we're going to choose one of the equilibrium to do it, okay? So we're going to do now 2, stability of the equilibrium. Let's choose one, okay? So which one to choose? Okay. Okay. So we choose the minus 1, the first one, doesn't matter, okay? We have to do them. Okay. So what we have to do, I'm going to write here the system. Okay, so what we have to do is to compute the linearization, okay? So basically that A matrix is done by the partial derivatives of the top and the bottom with respect to x and y. So for the top will be minus 6, right? So here, okay. So this is like ddx and this is like ddy, okay? So ddx of this fellow here would be minus 6 plus 2y, and that's about it, right? So I should move this up. Okay, but then we have to compute this at point minus 1, minus 1. Okay, I cannot just leave it with x and y in it. That's what I keep trying to tell you. Okay, now ddy will be just the 2x, but again at minus 1, minus 1. Yeah. Now ddx minus 2x at minus 1, minus 1, and the 2y at minus 1, minus 1. Okay, so what is A, right? The linearization, okay, or L or whatever. Okay, so we have to implement those numbers there. So we'll have minus 6 minus 2, it's a minus 8. Okay, that's a minus 1. Okay, minus 2, then 2, and then minus 2. Good. And now I'm doing the eigenvalues. Okay, So these are given by computing -8 minus lambda, -2, 2 minus 2 minus lambda equals 0. So we end up with -8 minus lambda times -2 minus lambda plus 4 is 0. So that's my way to do it. Okay, then we're gonna discuss for 3 minutes to do the delta and the P and the Q, I guess, okay? So this is lambda squared. And then we have here 8 plus 2, right? 10 lambda. And then we have a plus 20. Yeah, that's what it is. Did I do something wrong? No, it's good. So we have lambda 1, 2 to be minus 10 plus minus root of 100 minus 80 over 2. Yeah. So we have lambda 1 is minus 10 minus root 20 over 2. So this is negative. And lambda 2 would be minus 10 plus root 20 over 2. And I think this is negative as well, because root 20 is, so 4 squared is 16, 5 squared. So root 20 is in between 4 and 5, right? So there you go. Okay. And with this being said, we can already say that, you know, this -1, -1, it's a stable equilibrium. And it is a stable node, right? Or a sink. Because it has both eigenvalues, negative So that's my way of doing it, just because I know it, okay? However, if you want to use the table as is done in the book, here I'm doing this here, just like that, okay? So one should identify that this is actually A, B, C, D. And then what you do, right, would be something like, oh, let's compute delta. It was A plus D squared minus 4 AD minus BC, right? So in this case, you know, you should get the delta from there, 100 minus 80. So it will be 20, so it's positive, right? And then you do the P and the Q, right? So the first the Q was lambda 1, lambda 2. So in this case is AD minus BC. So in this case is 16 plus 4, right? So Q in this case is 20, right? So it's positive. And then P, right, which is in my mind is lambda 1 plus lambda 2. This was A plus D. So in this case, P is minus 10, so is negative, right? So now what I'll do, so I have these quantities of these particular signs, right? So delta positive, Q positive, P negative, right? And then I'm gonna flip to the table and look there what they tell me for these values. Personally, I really don't like this way, okay? Because it just proves that you can use a table and not think what you're doing, okay? But of course, you know, I cannot stop you to not do this. So we have delta positive, Q positive, P negative. So I'm flipping to the table. Probably I'll forget by the time I flip. Okay. So it was delta positive, P, I forgot, as I was telling you. Delta positive, where is it? Q positive, so we are on this side with delta positive, so it's either here or there, but with P negative, so P is here, so here, it's a stable node. So we called it a sink or stable equilibrium. It's the same thing. Yeah. So here, using the table, we fall into there. Okay, fellows? So, hey. Okay, there you go. So there's the, and then, you know, you have to do this for all equilibria, right? So at each one, you have to compute this linearization and, you know, what the sign of the eigenvalues is. Of course, you know, if this is just would be very straightforward. So our test won't be as such. So next time we're going to start doing some variations. But the algorithm, I think it's quite straightforward. Compute equilibria, compute the, you know, the linearization, compute the eigenvalues, discover what they are, or the sign and whatever, and then use a table or, you know, use your brain and figure out, oh, it's like E at 3t cos whatever. Okay, so it's unstable because it's a 3t's with power 3. So all these linear systems, right, because that's what we're doing here. From this one, we're going to the linear system, which would be, right, u, v, right, dot, well, actually, first in x and y. Okay, so this is minus 8, 2, minus 2, minus 2, xy. And from here, we're going to the uv with this eigenvalue. So that's the part from here to here is the linearization, okay, about this minus 1, minus 1. So in other words, we take this vector field here, this f and g, and we say, look, these two functions near minus 1 and 1, they're almost like this, right? Because it's coming from a Taylor series where we ignore terms of order 2 and higher, right? And then we just say close to that is happening in that. Okay, so this is this for today.